Welcome back to, now it's lesson 5 in Math260. Today's topic is scalar and vector projection. The idea is we're going to use the dot product, what we've learned about it, to be able to take one vector, u, and break it up into two pieces. One that goes along another vector, v, and the other part perpendicular to v. So this uses a little bit of trigonometry, but we'll develop it piece by piece. So first we want to remember the formula that we developed before. When I take the dot product of two vectors, the cosine formula tells me I can write it in terms of the length of the two vectors and the cosine of the angle. So I'll put the angle in here. And I'll call it theta, big letter theta. So the dot product is the product of the lengths times the cosine of that angle, of the angle between the two vectors. So that's a rule we saw before. Now how can we use this to develop what we're looking for? Well, one thing I want to do is I want to find the length of this base of the triangle that's formed here. That is the length along the vector v. Well, what does trigonometry say? Remember, the rules of trigonometry tell me that if I call the length of this hypotenuse c, then trigonometry says that a divided by c is the cosine. The ratio of the adjacent to the hypotenuse. But what is c? Well, it's the length of that vector. So that's the same as a divided by the length of u, because length of u is the hypotenuse of this triangle there. So to find a, the missing component, you simply solve this by multiplying both sides by the length of u. So a would be the length of u times the cosine of the angle between the two vectors. Now that's starting to look quite a bit like our formula here, except we don't have v involved at all. Well, we can't just multiply by the length of v because that will change the answer. But what always works is multiplying by 1. So what I'm going to do is multiply this equation by 1 instead. And that's still the same equation. But what I'd like to do is have this 1 be the length of a vector. Well, how do I get a vector that's in the same direction as v but has length 1? Well, if v has length 5, if I divide that vector by 5, that is multiply the vector by 1/5, I'll get a vector of length 1. If v has length 15, if I multiply by 1/15, I'll get a vector of length 1. So the way I get a vector of length 1 is I simply divide by its length. So I have this new vector, I'll call it v with a hat on it, which is the original vector divided by its length. So whatever length v was, dividing it by its length gives me a new vector in the same direction, because really what I'm doing is this is really just multiplying by a scalar. The length of a vector is just a number. And when I multiply this number by the vector v, because this number is the length, the vector I get has length 1. So now I can write this again as the length of u times 1, but 1 is the length of this new vector, v hat. And now this looks exactly like the form of a dot product. But it's not the dot product of u and v, it's the dot product of u and v hat. That is a dot product of u with the vector of length 1 in the same direction. So we can finish this up and say that A is equal to u dot v hat, and that's the same thing as u dot v, all divided by the length of v. So now we have a way using the dot product. Remember, we find the length of a vector by taking the square root of the dot product with itself. So this is really u dot v over the square root of v dot v. So using just the dot product, we've now broken this up. We found the length A that we were looking for. So in simplest terms, A is the dot product of u and v divided by the length of the vector v. So we're almost there. So we'll pause here for a second to capture this, and then before we do a numerical example, let's finish the development. So what I'm going to do is rewrite the final answer up here. The length of the base of that triangle is equal to u dot v divided by the length of vector v. And that's the same as u dot v hat, because v hat is the vector v divided by itself. Okay, so let's erase the rest of this. That was just the development. So now we have that. What I want to do now is make a vector that's just that length. So I almost need a new color, but I'll use green. I want to make a vector that's this length, exactly the length A. Well, how do I make a vector that goes in the direction of V, but has the length A, that is the length of the base of the triangle? Well, that's easy. If I want, I'll call that vector, what can I call it? I think I have a word for it in my notes. I'll call it W. So we'll call this green vector W. How do I make it? Well, W needs to be in the direction of V. Well, V hat goes in that direction, the vector of length 1. And if I multiply it by the constant A that I just found, then that's it. Because this is a vector of length A that goes in the direction of V. It's exactly what I want. It gives me the base of the triangle. So now, I want to make this vector also. I'll call it P. And now by my old rules of vector addition, what do I know? Well, if I take W plus P, by my head to tail rule of vector addition, what do I get? I get the vector U. So this can be computed directly because all I need is the dot product. A couple of dot products to get it. And U I started out with, so P is my only unknown. Well, by my nice rules of vector addition, I can add negative W to both sides. And I get cancellation. So P must be U plus minus 1 times W, or more commonly written, U minus W. So now I have a complete formula for breaking the vector U into two pieces, one that goes along the vector V and one that goes perpendicular to the vector V. And this is related to turning a vector into any coordinate system that I desire. So let's use these formulas and do an example. I'm going to erase the figure. And because it's hard to get nice numbers, I'm going to use the example we set out with in the book. I'm going to let U be the vector with components 8, 2, and v be my nice handy vector with components 3, 4. So the first thing I want to do is compute the length of, this is the scalar projection of u onto v. So I need to know the length of v. We start there. The length of v is defined using the dot product as the square root of v dot v. That's how I find lengths. Well, what is v dot v? It's 3 times 3 plus 4 times 4. That's the square root of 3 times 3 is 9, plus 4 times 4 is 16. 9 plus 16 is 25, or 5. So I gave myself an easy example. So now what would be the dot product? U dot v. Well, I can get my scalar projection by taking the dot product. U dot v, and then divide by the length of v. Well, u dot v is 3 times 8 plus 2 times 4, and divide by 5. 3 times 8 is 24, plus 8 is 32. So that's my scalar projection of the vector u onto the vector v. Now I want my w, which is this number times v hat. So let's get the vector w. It's going to be a 32/5 times v hat. Well, that's v, the vector 3/4, divided by its length, 5. Or in other words, 32/25 of the vector 3/4, which is finishing up. 32 times 3 is 96. 25ths, multiplying through, and 4 times 32 is 120. 3 times 4 is 12. 128 over 25. So that's my vector w, the vector that goes in the same direction as v, but has this length a. And then we need just a little bit more board space to get my other component. P is simply u minus w. And so my u vector is 8, 2, and my w vector is 96/25, comma 128/25. And I subtract. So 8 times 25 is 200. So 200 minus 96 is 104/25. And to convert this to 25ths, I have to multiply top and bottom. That's 50/25 minus 128. My arithmetic is good. So this is my vector p, and now I've broken my original vector u into two pieces. This one, the vector w, that goes along the vector v, and this one that's perpendicular to v. Okay, except it's important to do the arithmetic correctly. It's actually minus 78/25. So now what we want to do is prove to ourselves that P and U and W are really perpendicular. Let's redraw the figure. First thing I'm going to do now is capture the answer, the two answers. So we have that W is 96/25, comma 128/25. So that's my vector parallel to V. and P is 104/25 and minus 78/25. So now, if these two are really perpendicular, what do I have to get as the answer when I take the dot product? So we're not computing anymore, we're just actually verifying that we did the work correctly. If W and P are really perpendicular, then W dot P would better be 0, right? So what I'm going to do is cheat a little bit. I'm going to write it this way. That is, I'm going to take out the 1/25, and so I really have the dot product of 96/128 with 104 minus 78, with a 1/25 squared, or 625. So what is the dot product then of this? It's 96 times 104 minus 78 times 128. And a little work with the calculator should verify that is exactly 0. Proving that they are indeed perpendicular. You can verify that with your calculator. So this is the idea of scalar and vector projection. Used primarily to break up a vector, like the vector u, into two components. One in the direction of a particular vector, and the other perpendicular. Now, what is this useful for? Let's just sketch that as a conclusion. In physics, for example, when I have a body orbiting or in the gravitational influence of another object, like a comet or a satellite, I'm very often interested in two components of its motion. One along the direction of travel, and one perpendicular to the direction of travel under the influence of gravity. That's an example where I want to take a composite vector and break it up into two pieces. One that's in a certain direction, and the other one perpendicular to a certain direction. Okay, that concludes lesson 5.